you should know how these things work. But just as a quick summary for everyone else, this is an hour session, about 45 to 50 minutes of execution. I'll help you track the time since you're not focusing on that aspect today, and we'll get right to it. So, did you switch language? Oh, you did. Okay, we're doing Python. Okay, sounds good. So this is a problem where I would like you to write me a function called validPath, and it returns a Boolean. The inputs are going to be a integer in, a integer source, and an integer destination. These are all nodes, by the way. Nodes are represented by integers. And then you're going to be given a, let me just say, what is this type called in Python? I guess it'd be a list of integers.
Wait, sorry, we're getting a list of integers?
You're getting a lot of stuff. So you're getting like
Okay.
4 parameters. No, yeah, 4 parameters. You're getting in, which is an integer representing the number of edges, the number of nodes. Sorry, the number of nodes. You're given a source, which is the integer. This is a node. So nodes are integers. You're giving a destination, which is also an integer. Okay, and you're also given a list of integer, and this is a list of edges of the graph. Okay. And so how this list works is this is a list of 2 long lists where the elements are the source and destination nodes. And you'll be given a list of these lists. Does that make sense?
Wait, can you repeat that?
Yep, no worries. So you get one of the parameters given is a list of integers, which represents the edges of the graph. Okay. And so one edge is defined as a list where the first element is a source node and the second element is a destination node. That's right, yep. And you're given a list of these edges.
Okay.
Okay. And you are to return true if and only if there is a path between the source and destination.
Wait, sorry. What does the first parameter integer in
Oh,
represent?
it's a character in. It represents a number of nodes in the graph. You may or may not need it. That's up to you. Because you
Okay.
can deduce that by processing the edges if you choose to.
Okay. So, okay, just to reiterate, so this represents the total number of nodes.
Yep,
The
that's right.
source and destination, are these node structures or are they just integer values?
No, they're just integer values. So
Okay.
you have a node that's might be called node 1. You have a node that might be called node 17. The value of the node doesn't matter. We don't care about the values of nodes. We only care about the structure of the graph. So you can think of these as as like IDs almost.
Okay. And then this list of integers
Hmm.
is a list of edges that look like this, and
That's
then
right.
each of these are just values as well.
Yep. These are both
Okay.
ID integers. Yep. That's right.
Okay. So we want to determine if there is a path between source to destination.
Yep.
Okay. Okay. Um, Maybe let me think of an example first. So if we're given source one destination five, and then if we have an edge, so an edge would be like this, and then if we have another edge that's so then this would be a valid path, right? Because we have edges, and then at some point there exists a path between one and five.
Exactly. Yep.
Okay. Hmm, I see. Okay, maybe. Okay, maybe it would be helpful if I build an adjacency list where I map each node to a list of nodes that it's connected to. Like if I, so if I have, okay, wait, I have a question.
Yep.
Uh, wait, never mind. Okay, so if I so mapping like in this case I'd be mapping 1 to 2 and then 2 to 3 and then 3 to 4 and then 4 to 5. So I guess I could just okay, but then we could also have like other edges. Like a node can be connected to more than one edge, more than one node, right?
Yeah, definitely. Yep. It could
Okay.
also be connected to node like to no other nodes. It's also possible.
Okay. So what if I just iterate through this hash map starting at the source and then perform like a traversal on all of the nodes that it's connected to? So in this case, if we're starting at 1, then I would start at the first node that it's connected to, 2, and then I would look at this node's connections, which is 3. So then I would keep um, following the path that we're on until we reach the destination if it exists.
Okay, that's pretty high level, but I think you're on the right track.
Okay. Um, okay. But then, how would I do this?
So
uh,
you're definitely right in starting with the source node. That definitely makes sense. Um, right? And so let's say your source node, your example is 1. So you know from 1, you can get to 2 and 3, right?
yep.
Right. And
Yes.
so you know that wherever you can get from 2 and wherever you can get from 3, you could also get from 1.
Yep.
So you essentially want to say, hey, at my current situation, which let's say is 1, I can get to 2 and 3. And at any current situation, I can get to the nodes in my adjacency, nodes. Like, so like what do you want to call it? Adjacency list, graph, whatever, right? That's fine.
Hmm.
And that means that if I start at my source and I only go to nodes which I have access to, then if I reach a node, any node, I know that I must be able to have gotten it from my original source because that's how, because like from logic, we know that we only went to nodes that we had access to at any given time. So if we ever access
Right.
our destination node, that means we know it must be possible.
Right. That makes sense. So then if I ever encounter a node that is equal to destination, then I can return true. But how would I detect if how would I know to return false? Would it be like,
Hmm.
okay, so like say this edge doesn't exist. Like if this wasn't here, then I wouldn't have this in my adjacency list. And then I would end up at this node, starting at 1 eventually. And then I would try and check if 4 exists in my adjacency list and it doesn't. Wait, wait, actually, I have a question.
Yep.
Should I be like, so like right now I have it as like a like one way edge.
Okay.
Are these nodes supposed to be like this, like both of them are connected to each other, or is it only like one directional?
That's a great question. It is bidirectional. It is bidirectional, but for this problem, it wouldn't actually matter.
Oh, okay. So then that means that I would also have like 4 pointing to 3.
Yes.
Oh. So then, and if this is what my adjacency list looks like, then once I get here, then I'm gonna go to 4, and then I'm gonna check that 3 is there, but then I've created a cycle for myself.
Hmm.
Oh,
How do we detect
I
cycles?
mean, like if I don't know, like
Yeah, no worries.
if there's yeah.
Yeah, so if we let's say we start at 1, we go to 2 and 3, 2 we go to 3, 3 we go to 4, and 4 we go to 3, right? But we already visited 3.
Oh yeah.
So is there a way to
So we
say,
could just like if I have like a visited set, then I
mm-hmm,
could just store the nodes that I've already visited in this set, and then I'll only visit it if it's not in the set.
mm-hmm, yep,
Okay. So then I'll have like visit, and then as I'm traversing, I'm visiting one, two, three, four, and then I go to four, and then I see that three is already in visited, so I don't visit that. And
yep,
then,
exactly.
okay.
But you still haven't
So
answered the original
then,
question
okay.
of how do you know there's no path between the source and destination.
Yeah, and
So if we have,
that
so
is,
if you start at one, this is our, we say this is our, our adjacency list. We start at one, we visit at one, two, three, four, right? What other nodes
yep.
can we visit starting at one?
Oh, we could visit three.
But we have already visited three.
Oh, yes, we have already visited three.
Yeah. So
That's
like,
true.
what other nodes can we possibly visit starting at one? Is there a way to go to five? I mean, you said in this example, there's obviously no way to go to five, right?
Mhm. There's
So
no way to go to five.
yeah, exactly. Yeah. So how can we tell that just looking at our code though, right? How can we know that we have no more nodes that we could possibly visit? Because after we go here and we visit four, right? And then of course at four we check if four has any adjacencies. Four has no valid adjacencies, right? Like this is but it's not valid. It's already been visited, right? So our last
Hmm.
node that we could possibly go to are it has no valid adjacencies. In other words, we've exhausted all possibilities starting at one.
Yeah. Would it make sense if, like, after we visit a node, we delete it from the adjacency list? So then if we encounter an empty list, then that means we can't visit any more nodes.
Well, we don't need to delete it. Let's not do that yet, right? If like you're basically just redoing your visited array again, right, or set again. So we can just use that to track what we visited. But in addition, when we want to track what we visited, we want to track what we can visit next. Okay, so from node one, what can we visit? So I'll
Ew.
also say so let's try an example, right? So this is our state. Our state will have a visited, and our state will also have, what am I doing? We'll have next. Okay. So at state, we're looking at no, so our source, right? So our source is one. Okay. What is our visited set at this time? That's empty because we haven't visited anything yet, right?
Right, yeah.
Well, maybe you can put one
Okay.
in there because it's our starting point, right? So we visit our starting point. Okay, right? So what can we visit next at one? How many options are there?
There's two options,
There's two
two and
options.
three.
Yeah, so we can. There's two options. So there's two places we can go. What am I doing? There's two things we can do next from node one,
Hmm.
right? And then
Yep.
okay, well we haven't found our destination, right? So we got to keep going. Okay. So what's the next state gonna be? So next state is gonna be the next. So our first. So let's say we take two first. Without loss of generality, we could just take the first option, right? So now we visited
Hmm.
one and two. All right, and we got. And so we just visited one, right? So we just visited one. I mean two. Sorry, we just visited two. So two, we can't visit two again
Yep.
next, because there's already visited set, right?
Uh-huh.
So three is still an option, right? We haven't visited three yet. Three is still an option, right? Well,
Yep.
what else? What else? What other options have you unlocked by being at node two? Is there any new options?
No, there's only three.
Yeah, there's only three because three is already in our next array, so we don't have to add it in. So yeah, nothing to do here, right? Okay, great. Moving on. Now we take three because there's the only option right now. So we take three. We visited one, two, three. Okay. At three, do we unlock any new options?
Four.
Yep, four. So we have four in our options now, right?
Okay.
And then now we're at
Yeah.
four. We visited one, two, three, four. At four, do we have any options?
Three.
Yep, we have three, technically speaking, but we don't have to add it to our options because we can check the visited set before adding it, right? So we don't
Yes.
actually have any options.
Sure.
Okay, so we start at one.
Okay.
We have visited all the nodes we could possibly visit. There's no more options left.
Right.
What does this mean regarding the destination node?
So that means we cannot visit it because our options is now empty.
That's right, exactly. We've exhausted all the possible options from starting at source 1, and we still have not visited our destination node.
Okay, that does make sense. So in terms of this next structure,
Mm-hmm.
do you think it would make sense to use like a queue to add like nodes in there so that we process them in the right order? And then at the end, like if the queue is empty, then
Mm-hmm.
that means that we cannot visit our destination.
That definitely makes sense.
Okay. So, okay. So I'm gonna, okay, let me write down some steps. So I'm gonna start at source, add its neighbors to queue, and then I'm gonna iterate as long as queue is non-empty, add its edges to the queue, and then and then uh, add its edges to the queue along with visited. So as I'm visiting nodes, I'm adding the nodes um, edges to the queue, and I'm also adding the current node into visited, and then I'm gonna check if destination is reached and then return true. And then if we never return true and the queue is empty at the end, then we'll return false. Does that make sense?
Yep, sounds like a plan.
Okay, I will get started then. I'll call it uh, valid path. So we're passing in n and then a source, a destination, and a list of integers, edges.
It's a list of integers, right? But yeah.
Right, yeah, a list of integers. Okay, so um, I'm gonna build the adjacency list, which will be, I'll use a hash map. Oh, can I use this?
Yeah, you can. You have to
Duct.
import it though.
Okay. Mm, Collections? Is that how it works?
Yes, it is. Yeah, that's right.
Okay. Okay. So then I'm gonna iterate through the edges. So I'll do for um, node one edges, and then I'm gonna add it to the hash map. I'm gonna map this node to node two. Okay, so then now we have an adjacency list that looks like this.
Mm-hmm.
And then I'm also gonna add visited set, and we want a queue. So I will declare that. Okay.
You need to import
Okay,
that as
so
well.
we want to start from, oh, I don't actually know this import.
It should be from collections as well.
Deck?
Yep.
Okay. Okay, so then we want to start at the source. So I guess I will append that to my queue and source. Okay, so then now our queue, so like if we're using this example, then my queue would just have one in it.
Mm-hmm.
And then I'll also append it to visited dot add Okay. And then I'm gonna iterate as long as the queue is non-empty. So while queue, I'm going to pop from the queue node equals, and then I will add all of its neighbors. So I'm gonna do for neighbor in adjacency list at the node. I will append that to the queue. Append neighbor. Okay, so in this case, now the queue would have 2 and 3.
Mm-hmm.
2, 3. Okay. I guess like before I append neighbors, I could also check if the node we just popped equals destination. Then we return true because that would indicate that we've found a valid path from the source to the destination.
Yeah.
Okay. And then okay. Okay. And then I need to add these nodes to visited as well. So I'm gonna add that. I think it makes sense to do it here because after we've popped from the queue, then we've visited that node. So I can do that.
Fair enough. Yep.
Okay.
And what if it is visited? Then what do you do?
Oh yeah. Um, I guess I could check that here, like before adding a neighbor, I would check if that neighbor is already in visited, then I would not need to add it. So
Mm-hmm.
if
Yep.
neighbor in visited, or I'll do not in, wait, yeah, if it's not in visited, then we're appending it to the queue.
Mm-hmm. Okay.
Okay. Mm, okay. So as we're doing this, we are appending all the neighbors, and then at any point, if we reach the destination, we're returning true. Um, and then at the same time, if we don't have a valid path, then this queue would eventually become empty. So then I think at the end we would return false.
Cool.
Uh, I don't think I should be adding the source here because I will do that once I'm inside this loop. So I'm gonna delete that. Yeah.
Okay. Are you done?
Okay. Maybe I should run through this example again just to make sure.
Yeah, that's a good idea. Let's do that.
Okay. Um, okay, so I'm using this as my example. I'm gonna let me finish building this. So two is actually connected to one and three, and then three is connected to two and four, and then four is connected to three. Okay, so this is what our adjacency list looks like. I'll just put that like here. Okay, so then I am appending the source to the queue, so that's one, and then I'm doing while queue, and then I'm gonna pop from the queue, so one, and then I'm also going to add to my visit set, and then I'm checking if the node that we just popped is destination. It's not, so then I'm gonna get all of its neighbors in the adjacency list, which are two and three. And then I'm checking if they're in the visit set. They are not. So then I'm going to append that to my queue. I'm going to append both of them to the queue. And then I'm going to pop the two. and then I'm gonna add it to the visit set, and it's not the destination, and then I'm gonna add um, two's neighbors, which are one and three. One has already been visited, so I'm only going to append the three. Wait a minute. Wait, append three. Wait, that kind of does not make sense because the three is already in my queue, but uh, it's also the neighbor of two. So it doesn't really make sense to put it there twice.
That's true, but does it do any harm?
Uh, I mean, it's kind of weird because I'm processing it twice, which means I'll be adding its neighbors twice as well. So I don't know. It's
Okay. How can you prevent adding three to
mm,
the queue?
I could just like if I move this inside here. Wait, let me think. If I move this inside here, I think that would prevent that because then when I'm at the one, I will have added both the two and the three to the visited set. So then once I reach two, um, it's already in visited, so I don't have to append it again.
Yep. Yep. That would work.
Mm, okay, that makes sense. Then I guess I do need this here. Because I need the visited set to start with one.
Mm-hmm.
Okay. Okay, anyways, where was I? So I'm at one, I'm appending two and three to my visit set. And then okay, then wait, sorry, my Siri just went off. Okay, so now okay, I'm gonna start again. My queue looks like this. I'm starting with one, and then I'm adding its neighbors, and then I'm popping the one, and then I'm going to uh, two and three, which have been added to the queue. And then I'm looking at two's neighbors, and I'm not appending these again because they're already in the visited set. So then I'm popping the three, and then I'm checking its neighbors. The two has already been visited, so then I'm only going to add the four. And then the four only has a three, but that's already in the visit set, so then I don't do anything. And then this will return false after the four has been popped. So I think that makes sense. And then if there were like another edge from like what was it, like five, then I would append the five to the queue. And then once we pop the five here, then we check that we've reached the destination and return true. I think that makes sense to me.
Yep. Okay. Yeah, that makes sense to me as well. Let's talk about. Excuse me. I think this is getting to me. Let's talk about the time and space complexity of this algorithm.
Okay. So in terms of time complexity, uh, okay, so this is happening in, so this will run, um, this, like the length of edges, like however many edges there are, which, how many edges can there be at most? Let me think. So at most, we would have like all of the nodes connected to each other. Um, what? Okay, so then,
That's true, but what is this condition? So I guess this is
if
two things here,
neighbors
right?
not.
So the first thing is Time and space complexity to generate your adjacency list. Okay.
Yeah.
So let's talk about that first.
Um, that is interesting. Uh,
Interesting. I
I
have
don't
a.
really know how to
Okay.
describe this. Like,
Okay.
how would I know? Okay, so
Okay.
if we're given n nodes,
Okay. So we have. So
uh,
let's call this. We have n nodes and m edges. How's that sound?
okay, let me write that down. N nodes and m edges. Then this would run in O of m time because we have to iterate through each of the edges.
Okay. Okay.
Oops. O of m. Okay. And then
And then
for
space
this
complexity.
part,
No, hold on. Before we move on, what's the space
oh,
complexity of this guy?
um, so for each,
How many keys in your dictionary?
I'm gonna have n keys
Okay.
because there's n nodes.
Yep. And then
So
for
then it
each
would be O of n
and then
for
for each
space.
and then for each key, how many values are in your list?
Would be up to m edges.
Well, m edges in total.
Oh, yes.
So what's
But
the
okay. Uh, would it be n plus m?
okay? Okay, let's talk about the rest of the algorithm then. So time and space for the rest.
Hmm. So I'm iterating through this queue, but at most the queue, like each node will only get processed once. So the time would be O of n for each node. Um, yeah, I think that makes sense. Because we're only adding each node once and like we're checking if we've already visited it, so that will prevent us from adding it more than once. And then in terms of the space complexity, uh, we're adding it to the queue. So if we have like a node that's connected to all of the other nodes, then the space complexity could be at most O of n if we have to add all of the node's neighbors into the queue at once.
Okay.
And then the visited will also be O of n because we will have visited all of the nodes by the end.
Okay. Um, we'll comment on that later. For now let's go for a follow up question because we actually have some extra time. Um, Now let's modify. So first what we'll just save this thing. So let's copy it and make a new one. Oh, what did I do? Whoops. So let's
Oh,
copy this and
okay.
make a new one, like so. Call valid path 2. Now I want you to modify this. Oh, wait, no, I want to modify this function to not return a boolean, but to return the actual path.
Oh, okay. Uh, okay. Let me think. So I'm starting at 1, and then I'm going to 2, and then I'm going to 3, and then I'm going. So I'm processing the nodes in this order, which is the order at which I'm adding them to the queue. So I guess like I could also have. Wait, do we want to print this out as an array? Like, is that how you want it to be represented?
You can return it as an array of numbers. Yeah, that's fine.
Okay, yeah. Um, so as I'm building this queue, I could just add each of the nodes to the array, but Would that always work? Like, because like I could be going down a path, but it's like the wrong path. So then I would need to delete from my array.
Yeah, the array wouldn't be correct in that sense.
Um, hmm. Yeah, I don't think it makes sense to use an array. Um,
So one thing to note here is like your queue is was previously storing a node,
yep.
right? How about we store paths instead?
Oh, I see. Okay. So then if I were to store the path that we're going down, it'd be like 1, 2, and then 3, 4, 5. But I could also be going down like 1, 3, 2. What if there's like multiple paths that lead to the destination?
You can return any one of them.
Hmm. Okay. Okay. Um, but if we're storing paths, then how would I know when to pop from the queue?
Sorry, say the question again.
If I'm like storing the paths
Uh huh.
inside this queue,
Yeah.
then how would I know when to like pop from the queue? Like, how would I know what node I'm currently at?
Well, the last node in the current path is where you're currently at.
Hmm, true. And then once, I guess like the stopping condition would still be the same. Like if the most recently appended node is the destination, then we just return the path.
Yep, that's very similar. Very similar stopping condition. Yep. So the thing you would change here is
Um,
well, obviously to change this code probably, and you would probably want to rename this variable, and then we can go from there. How's that sound?
okay. So, okay. Wait, but why, oh wait, because I'm now appending a list. So I'm
Mm-hmm.
gonna be
Yeah,
like
exactly.
list. Okay.
Okay. And then
Mm. Okay, wait. So then instead of popping this whole list, I just want to pop the last element, right? Or
you,
like I
you
don't
still
want to pop it
you
because
still want to
I
pop the
just need to
list.
access it.
Yeah, I
Oh,
mean you still want to pop it because you want to re-add the list on later.
oh, okay. I'm gonna pop it. I'll call this path then. If
Mm-hmm.
so, then instead of checking the node, I'm checking the last element of path.
Yep.
If the last element is equal to destination, then I'm returning this path, which represents the array of the nodes in the path. And then for each neighbor in the last element's adjacency list. I'm checking if it's not visited, and then I'm adding. Oh, wait. Was I always adding node? I think I meant to add neighbor.
Yeah, it's fine. You were, but it's fine.
Okay. Okay. Then I'm going to append to the queue. Uh, wait, what? Let me think. Undoing. So I'm appending to the list. So that would be like that, I think. Would this queue ever contain like multiple paths?
It definitely could.
Mm,
I mean, we have like, so you already popped the path off the queue.
uh-huh.
So to make a new path, we want to, add our neighbor to this path, and then
Oh,
push the
right.
entire path onto the queue.
Okay. And neighbor. Okay. And then I'll append the path instead.
Okay.
Okay.
Any concerns with the solution?
Um, like, I don't really know if this condition makes sense because if we have multiple paths, then like those paths can have like the same node in each of those paths, right? Like, I don't
That's right.
think it makes sense to have like one global visited set.
Yep, that's a good intuition.
But like, how do I fix that? Like, that doesn't even make sense. Uh, um,
Do you have any ideas for how to fix that? If you don't, we'll move on. But
I don't know. Like, maybe if like each path had its own visit set.
okay, that's one way. Yeah, but let's not do that. That's too complicated. Okay, let's call it here. Let's call it here. Go over
Okay.
some notes, some review, and then we'll talk about it. How's that sound?
Yeah,
Okay.
sure.
So I mean, you know the drill. First thing I always ask is, how do you feel? What do you think went well? What do you think didn't go so well?
I mean, I needed some help on a lot of things because I'm not really familiar with graph questions,
That's fair.
but um, I think once you gave me some hints, it made sense. It was okay.
Yeah. Okay. No, I think that's a pretty accurate general assessment, right? So obviously we're unfamiliar with the graph space, and that's fine. But once hints were given, you were able to pick up the hints pretty quickly, and that's a very positive sign as well. And also, one more thing that was good was that you spent time to understand the problem and to to figure out exactly what we needed to do to accomplish that. So I think that overall I think is a good sign. Um, yeah. So the first
Okay.
problem is and this is a pretty general class of problem, which is basically finding properties about a graph, right? So basically all graph problems are some variation of this kind where there's a property about a graph. In this case, are two components connected, are two nodes connected, etc. Um, and it all comes down to various different algorithms you can apply to this graph to find the solution. And depending on other properties of the graph, different algorithms might be more or less efficient. So that's kind of the skill curve, you could say, of graph problems. The
Hmm.
first problem was a pretty standard, I would say, you know, path finding algorithm, right? But in this case, you don't actually need to find the path. You can just find any path, right? And so, and again, you weren't familiar with this, and that's okay. But the hints I gave were essentially the intuition for how a breadth first search would work. And I was very careful to not use any of that terminology, but instead to just explain how things would happen under the hood. And I think this is how effective teachers teach it anyway. So, keyword teachers aren't, in my opinion, aren't it. But, right. So the intuition I gave was about, in this case, how you might have these two pieces of state, right? So if you scroll up again, these two pieces of state, so the visited
Hmm.
and the next arrays, or sets, what do you want to call them, right? And after this intuition was gave, you seem to understand how we should, interact with these two pieces of state. So I think that in itself is already really encouraging that like you were able to kind of carry that torch forward from that point, right? And you actually had some pretty good
Hmm.
questions. Like for example, a question you had that was good was, what if there's a cycle? That's a very good question. Now, obviously, it's better to ask that before we get there. It's and this is true for all types of problems, by the way. Whenever you see a problem of a certain class, there should automatically be questions that come out. So, for example, for graph problems, things like, for example, is the graph directed? And this will be asked: can the edges go both ways? This property is called directedness, right? So this is a question you should always ask: is the graph directed? Does the graph have cycles? Are there weights? Are the weights be negative? Right. So for graphs, there's these set of problems. For example, questions where the return value is like a list, there should be like, hey, does the ordering matter? Does this matter? What type is the element in the list? And so these kind of things, right? So as you get more and more familiar with graphs, you should get more and more familiar with the types of questions you should ask right off the bat. Because for more complicated problems, the difference between knowing and not knowing these properties could be a very, very big difference maker, right? So, but that's not really a
Hmm.
slight. I think you get better at that as you practice. But I think just based on what I've seen today, there's already good intuition based on that. Okay, so um, yeah, and another piece of this one I saw was that you decided to use a queue for the next array. Now, for the
Hmm.
specific problem that we were working on, it actually doesn't matter what type you used. You could have used a set as well. That would have also worked. But because you used a queue, I said, oh, okay, well, she understands what we're trying to accomplish here. We want to go in order because that prescribes some efficiency. That makes sense. And because you used a queue, I thought, hey, it'd be appropriate to ask the follow-up question like I did because that one also benefits from having a queue. One thing I will also encourage you to do, which you did do, but I would encourage you to do it even more, is when you're writing a solution note, like in your first time, and you weren't sure what things were happening, I would definitely encourage you to do what you did, which is when you wrote these comments, kind of telling yourself what state these should be in. And I'd say, especially for when you aren't familiar with a problem or a type of solution, it's really really good to spend time doing that. Like it's not a waste of time at all because, well, first of all, it helps mitigate against bugs, but second of all, it also really helps. It saves you some time later on when you do like a walkthrough of the test case, right? So it's definitely not a waste of time
Okay.
to write those things down. So I
So,
would,
so you mean I should be doing this like while I'm writing out the solution and not just at the end?
yes, if you're not familiar with it, right? So for this
Okay.
problem, which you weren't familiar with, it's definitely okay to do that because you would have done it anyways afterwards to walk through the solution. So I
Right.
think it's
Yeah.
it's a pretty good use of time. Okay, excuse me, get some water. Give me a second. Okay. Um, time and space complexity. So uh, it's a bit off. It's a bit off. Obviously, I think okay. There's two things to say here. First of all, is if you go and study graphs, people I recommend this to people like just memorize the time and space complexities of all the common algorithms, right? So this is a BF. This is a very very standard breadth first search. Breadth first search complexity for time and space is edges plus nodes. And I recommend people just memorize it because you're gonna fumble when you're trying to figure it out, right? But because you didn't know that,
Okay.
I think you did pretty good considering the fact you didn't know that, right? So for example, I'll give you a couple pieces of intuition off the bat, right? So when you generate the adjacency list, um,
Yeah.
one thing you forgot to take into I gave you a bit of a hint, but I don't think you picked this one up exactly. Is that the space complexity is the space complexity of this adjacency list, right? You have in keys, which is correct. You have in keys, and then for per key, so it should be right. So you have space in, so you have in times space per key, right? Space per key, right? So how much space
Right.
are you using per key? Well, I told you there's m edges. There's m edges, right? And so on average there should be how on average should be m divided by n, right? Uh, edges per key because there's m edges in total.
Oh
So
yeah, yeah,
right,
I see what
so
you mean.
yeah, so some details there that you can definitely expand upon. Now, in general, if you weren't given some hints about this one, yeah, just go memorize this kind of thing and don't figure it out on the spot, right? Because first of all, it's a time saver, and second of all, if you're not gonna like, okay, I should be clear about this. BFS in general is edges plus nodes, but there can be restrictions or special assumptions given on a certain problem, which can make the solution much more efficient or much less efficient. So the v plus. Oh, and by the way, it's usually notated as v plus e. V being the number of nodes, vertices, and e being the number of edges, right? But n plus m is fine. I just use the same v plus
Okay.
e, right? But if you start from the v plus e as like a base, and then you say, oh, it's v plus e typical for BFS, but we have a special condition here where blah 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 blah, so it's actually v plus log e or something, right? And so, so start with the basics and then say, hey, is my problem different? Did I do anything different in my BFS? And if so, then you can change it. If not, then it's just v plus e. Um, in your analysis, oh, I don't see where analysis is anymore. So one thing you forgot to account for in your analysis for the time complexity here again, by the way, is it's in nodes, correct? It's in nodes, but for each node, you also have to scan through the entire adjacency list, even if it is already added to the visited array. You can't know that before looking at the adjacency list itself.
Oh,
So that's a factor you
true.
forgot there. So that's why yours is too low, and it has no m in it, right?
Okay.
Obviously, the number of
So
edges does
then they
matter.
should, so like, should the time and space complexity all be like n plus m,
Yeah, overall, this
or
problem will
like
be
both
n
of
plus m.
these?
Yeah.
Oh,
I want to spend a bit of time here before we end time to talk about the second follow up, by the way, and then we have time. I'll have time for you to ask questions, but I want to get to this question because
okay,
these
yeah.
two kind of things kind of are symbolic of the two types of graph traversals, right? So one type of graph traversal is X possible? Is this property possible? Right. That's the first question we asked. Right. The second question is, if it is possible, give me the actual solution. Right.
Right.
And that is a subtle difference. Right. You can see it's basically the exact same algorithm. Right. Basically the exact same one, but you can see the queue. The state is different, obviously, and of course, some things are also different in the context of why we're doing something. So you did again, very good intuition. You noticed that the neighbor check doesn't really make sense because we can get to the same quote unquote neighbor from different paths. So again, that's very good. That's very good
Yeah.
intuition, but you didn't quite have the intuition then to how to solve it. So I see you're about halfway there, right? So, but that's a good sign because once you do study it for real, then it should come pretty naturally, right? But why do I bring this one up? Because this is a common follow up problem. Like not this one specifically, obviously, but if a question is phrased as like, hey, return a boolean if X property is possible. When you're asked that question, you should be prepared for a follow up of like, oh, okay, the follow up, the very very easy and common follow up is like, oh, now actually show me the real solution, right? And why do I say that is because
Right.
part of the solution there is like, do you recognize that it's the same problem, it's the exact same thing, but the state is different. It's the only thing that's different, right? So whenever you're studying these graph problems, you're studying these solutions, be very very clear what the state is, because that will be the only thing that varies. The algorithm, BFS, DFS, Dijkstra's, Bellman-Ford, all these things are the same algorithm across all graphs, right? It's just that the state that you track is different. So this problem that and of course I gave you a bit of hint on this one. We want to store the path instead of the node. Once you recognize that, and that will come naturally as you study the problems, but once that hint was given, you were able to solve it basically by yourself, right? And so just recognize that that's a very
Hmm.
powerful piece of insight. Is that there's every time you're asked, hey, is something possible, the second question will be like, okay, no, actually do it, right? So this
That
is your
makes sense.
basically your head first dive into the deep end for graph problems. I think considering you haven't seen these kind of things before, I think you did pretty good. So pat on the back for that. Good stuff.
Wait, is this considered an easy question? Because I feel like it's kind of hard.
This would be considered an easy question in the graph world, but graph questions in general are
Okay.
harder than other questions. So this would be considered easy graph problem,
Yeah.
but probably like a hard tier easy or an easy tier medium in the space of all problems.
Right. Okay.
Yeah, and it definitely felt hard because you didn't know about this pattern, like the pattern of set up the adjacency. I mean, you knew this one, but you didn't know the pattern of set your visits at your queue and then do this immediately, right? So a problem like this is a very what I call a pure problem, where there's the only thing that's being tested is purely your ability to regurgitate a BFS. Now, that's accounted for in the difficulty ranking because people who do these kind of problems know BFS. Like they know the thing very well, right? But if you don't know BFS, then it is going to be a much harder problem because you had to build this without the intuition of BFS. So that's why it felt hard. But know that once you start doing more and more of these graph problems, this type of pattern is very common, and you'll find it easy after a while.
Like, okay. Can I ask questions
Yeah,
now
of
or
course. Yeah, go ahead.
could you also solve this using DFS and would that be better or
Yep, you can solve this problem using basically any traversal. So any of the graph traversal algorithms would be able to solve this correctly. The only difference would be the efficiency. So um, so yes, you could. So yes, you could use DFS. You could use BFS. You could use Dijkstra's. You could use a bunch of there's a lot of algorithms you can use. A star's a one. There's like a bounded DFS, stuff like that. Like all of these are all possible. It's just a matter of do you recognize which of these is the right choice to use for the particular problem.
okay. Would it be like more or less efficient if I use DFS?
So in this case, it would really. So in this case, it's not clear because I didn't give you enough information.
Okay.
So you would have to, for example,
Oh,
know the light. So the difference in DFS is that it could be better space complexity if the path is short. It could be. So by path I mean the final solution. So but
mhm.
because that's all information that was given, you can't assume that. Right, but for example, if you knew these out, you might ask, "Hey, do we know anything about the length of the path?" You might ask that. And now, obviously, I wouldn't tell you because that's not the problem. But right, but you could ask that, and I say, "Oh, this person is smart. They're considering using that. They're considering using that." So there are different trade-offs for that kind of thing. But in this particular problem, the answer is no because they didn't give any information.
Okay. Also, like, why did you give me N? Because I didn't even end up using that. Would there
Uh,
be like a solution where I would have to use this variable?
yes and no. There's a couple things that the reason that you might use in is because look at your adjacency list. Your adjacency list is mapping a node, which is an integer, to a list of integers. You instead could have just defined your adjacency list as a list of how do you write a list again? Is it like this?
Yeah,
So you could
yeah.
have just done that instead.
Oh,
Oh no, not that. Sorry, I meant I
oh,
meant I meant this. No, wait. Oh, yeah, how does Python work? You know what I mean? Like you can make it. Oh no,
I
I think it's
see.
this, right? I don't know, but
Yeah,
you know
I
what I
think
mean. Like you
so.
could have done this, right? Some languages
Oh,
this would have
okay.
helped you. Would have helped, but yeah. So yeah, again, right? So and I by the way, I copied this signature right from Leetcode. So this is just a signature that's given to some languages, which might find that useful. But yeah, like and you'll see this sometimes, and I gave you this hint specifically because I know you're doing Python, but I said you might not need this variable because yeah, you could calculate it if you needed to. You could calculate it by processing the edges anyways. So it wasn't needed, but it's still provided.
Okay.
Okay. Anything else?
No, I don't have any more questions.
Okay. Cool then. Then let's call it here.
Okay, cool. Thanks for having me.
You're welcome. Thanks for participating.